So you already know by this time there are some basic strategies of exploration. For example, the Q-learning and DQN and SARS and all those value-based algorithms Zoo exhibits, they try to take either a best action with probability 1 minus epsilon or a random action with probability epsilon. And this basically formally solves the exploration problem, because eventually they're going to find the optimal policy. Or will they? Another strategy which looked a bit more advanced, although it's just as heuristical, is the so-called Boltzmann exploration strategy. Again, I'm sorry. In this case, you want to take your Q values and make them into something that looks more like a probability. In deep learning, you know that if you have some arbitrary values, you can make them into probability by applying softmax. And, multiplying or dividing them by some coefficient to account for how ruthlessly do you want your agent to explore. We also had some methods with built-in exploration. For example, cross-entropy method and the policy gradient method family, like reinforce or actor critic, they all learned the probability of taking action explicitly. And you could, of course, affect them with adding with a regularization of entropy or something similar. But in general, the algorithm decides its exploration policy for itself. So now to see how all those exploration strategies fare against our newly invented notion of regret. Let's begin with a simple one. This time we're gonna explore with an epsilon greedy policy, with epsilon precisely equal to 0.1. This means that at any moment of time you have 10% probability of behaving randomly, and 90% of picking whichever action is maximizing the Q function you currently have, the imperfect one. I want you to answer me this question. Have this notion of regret, which can be treated as a function of time, up to which you add up those coefficients. I want you to tell me what's going to happen with regret for this epsilon greedy strategy. So what's going to be the curve which represents the stacked difference between epsilon greedy policy, learning over time, and the optimal policy which picks the action with highest return all the time? Well, yes, unfortunately it's the worst possible case. It's going to grow linearly. And the reason here is that if you explore with a constant epsilon of 0.1, it means that even if you have found optimal policy, if you have found true Q values, then you can still not get the optimal policy out of it. Because at any moment of time, you're going to explore, and some of this exploration is going to be bad for you. So this basically means that your exploration your regret is going to grow linearly, because there's going to be some constant offset between 0.1 greedy strategy and the greedy one, which is the optimal, which is going to stack and grow and grow and grow again until it reaches infinity linearly. So this is a bad scenario, and surely we're going to fix it with some of the duct tape we've been learning all over the previous weeks. How do we treat this epsilon greedy policy better so that it converges to something, to a constant regret? Yeah. So, of course, there's more than one way you can do that, but the general pattern is that you have to start with some fixed epsilon, and then decrease it over time. And there is a notion of so-called greedy in the limit strategy, which means that your exploration eventually converges to an optimal greedy policy after infinite number of time steps. For example, you could start with epsilon equal 1, or whatever number you prefer, and at every time step you could just multiply it by 0.99. This constant is, of course, dependent on a particular setting, but this means that at no fixed point of time will your algorithm terminate the exploration and get exploiting. But formally, in the infinity, it will asymptotically converge to a greedy policy. This is theoretically good because it allows you to babble about how your algorithm's regret is converging somewhere, of course, provided that it is able to learn optimal policy in this region. You've also seen some other mechanisms. For example, the classical deep Q network, the DQN, uses not this multiplication by some constant which is near 1, but the linear trajectory where it subtracts some constant value from epsilon until it reaches 0 or some small constant value. Theoretically, it's less than perfect, because if you're linearly decreasing epsilon, then if you have reached 0 epsilon before you've gone to the optimal strategy, your regret is going to grow because you have not learned the optimal one so far. But again, in reality, it doesn't matter that much. So this is basically how regret works in terms of the strategies we've already been using from week 2. You could also take, say, Boltzmann exploration policy. You'll find out that if you use the same strategy with tau, if you start with constant tau and then decrease it over time, then you'll devise the strategy which is greedy in the limit in terms of this Boltzmann exploration policy. It may be better or worse than epsilon greedy depending on a particular environment and a particular regime you're using. So this is basically a duct tape challenge where the winner is not that much a theoretically better algorithm, but the one that's just slightly better fits this particular problem. Instead, I want you to focus on something, well, qualitatively different. I want you to, and I'm gonna get you through some of the algorithms that explicitly pick actions that are most interesting to our agent. This is precisely the topic of our next section.